This bridge was 4 months old. On the morning of November 7, 1940, a crosswind of roughly 40 miles per hour struck the Tacoma Narrows Bridge in Washington state. The roadway began rolling in waves. Then the motion changed. One edge rose while the other fell, up to 28 feet, tilting the deck as much as 45 degrees every 5 seconds. By 11 a.m., the center span was tearing itself apart. The wind was not unusually extreme, and the bridge had not simply been built too weak for traffic. The deeper problem was that its shape allowed the wind and the structure to enter a self-amplifying loop. The original state design was conservative. Engineer Clark Eldridge proposed a 25-foot deep open stiffening truss beneath the roadway, but federal funding brought in a nationally respected suspension bridge consultant, Leon Moiseeff. His revised superstructure stretched the center span to 2,800 feet and replaced the deep truss with solid steel plate girders only 8 feet high. The result was elegant, light, and inexpensive. It was also extraordinarily slender. The center span was 72 times wider than the distance between its cables. The Golden Gate Bridge's comparable ratio was 47-1. Moiseeff's design was strong enough to carry its expected traffic, but strength under a static load was not the same as stability in moving air. The warning appeared before the bridge opened. As workers finished the deck in May 1940, it began rising and falling in the wind. Some workers chewed lemons to fight motion sickness. On opening night, the bridge began to gallop again. Engineers installed hydraulic buffers at the towers. They made no noticeable difference. Tie-down cables reduced movement in the side spans, but not in the center. Professor F.B. Farquharson began wind tunnel tests. His scale models sometimes shifted from vertical waves into a violent twist. He warned that if the real bridge ever copied that motion, the bridge would be finished. He recommended cutting openings through the solid girders or adding curved fairings to guide the wind around them. The study was complete. A retrofit contract was being prepared. The bridge failed 5 days later. At 7:30 on November 7th, the wind measured 38 miles per hour. 2 hours later, it was about 42. At first, the bridge performed its familiar up and down wave. Traffic was stopped, and people struggled off the moving deck. One car remained stranded with a dog inside. Shortly after 10, a cable band near midspan slipped. The roadway separated into unequal moving sections, helping the motion change from vertical bending to torsion. Within minutes, the bridge was no longer moving as one flat ribbon. One side climbed while the other plunged. The twist repeated again and again, each cycle forcing steel, concrete, cables, and connections through reversals they had never been designed to survive. Just after 11, floor sections began dropping into Puget Sound. The center span followed. Everyone had escaped, but the dog did not survive. The common explanation is often called resonance. That is incomplete. The bridge's solid 8-foot plate girder presented a broad face to the wind. Air separated around it, creating pressure differences and swirling flow. A small twist changed the deck's angle to the wind. That changed the airflow, which added more lift and torque to the next twist. As the deck tried to return, its motion and the aerodynamic force became synchronized. The bridge was no longer merely responding to gusts. Its movement was organizing the wind force that drove the movement. Engineers call this self-excited torsional flutter. Once the energy entering each cycle exceeded what the structure could damp away, the motion grew. More twist reshaped the airflow. The reshaped airflow created still more twist. The feedback loop continued until the deck exceeded its structural limits. The collapse ended an era of ever lighter, narrower suspension bridges designed without a full aerodynamic model. The replacement Tacoma Narrows Bridge, opened in 1950, used a much deeper open truss. Wind could pass through it, and the structure resisted torsion. Engineers tested its behavior in a wind tunnel before construction. Today, long-span bridges are streamlined, stiffened against twisting, or both. Wind tunnel testing and aerodynamic analysis are standard parts of the design process. Tacoma's lesson is larger than bridges. A structure can satisfy every expected static load and still fail when it interacts with a moving environment. The wind did not find one weak bolt. It found a system that could feed energy back into itself.